Telescope, which is arguably the nation's biggest investment in ground-based astronomy at the present time. And if you want to play Where's Waldo, there I am in that picture. So I've gone through this progression of small group science into big project science. And when this Rubin project got started, I was the original project scientist. The first proposal that we wrote for the National Science Foundation, we wrote in 2003 with 4 people sitting in my office here at Harvard, and it grew into this big thing funded by the Department of Energy and the National Science Foundation. And learning how to make that project succeed, gathering the community support, raising the money, keeping it going, has been an interesting professional transition for me. It's not just in the field of astronomy that we see evidence of ever larger teams. If you just look across the entire academic enterprise, the definition of large varies from subfield to subfield, but there is, I think, incontrovertible evidence that team sizes are getting larger and people are trying to do harder things in larger groups. This is an interesting color-coded chart where columns denote number of authors on papers, and it's sort of a heat map of how those fingers of collaboration extend to the right across different fields. And so if you look up and down here at the very top row, maybe no big surprise, mathematicians tend to write fewer co-author papers than people in physics, which includes particle physics that have occasionally papers with thousands of co-authors. But I think there is this inevitable trend towards the right of team sizes getting increasingly larger. You might ask, well, okay, so if that's true, if you had some definition of optimal, what does the optimal team size look like? And people have certainly started to ask that question. I think it depends a lot on your definition of optimality, but you could imagine defining a metric and then looking back and asking which of these papers are more impactful, the ones with lots of authors, and should you divide by the number of authors? How do you normalize it? How do we do bibliometrics? That's all pretty tough. But I think it's fair to say that the things that are really hard are hard for 1 or 2 people to do at this point. I think there is this sense in science that the single isolated genius having a eureka moment is, I think, a historical holdover of some impression of success. And I think there's certainly ample opportunity for creative individuals to have large impact, but I think that's a little bit of an outdated notion. I think we need a broader definition of success in the enterprise writ large. So after having had a number of discussions with people in my research group and trying to mentor people in this large project, there was one Thanksgiving weekend where we went off to Colorado into a timeshare, and I just sat down and in about 4 days flat tried to write down everything that I thought I had learned. And my way of saying it is, this is the book I wish someone had handed to me when I first started embarking on a big project. And it's an attempt at writing down just all the stuff that nobody ever bothers to tell you explicitly. We're not trained in the sciences. When we get a PhD, it's not like someone tells you, here's how these big collaborations work, and here's how you can find your way. So I think maybe this book is the reason I'm here before you. And let me just tell you that in return for my foregoing any royalties at all, MIT Press agreed to make a PDF version of this available for free. So if you click on the thing on the left, you'll go to a place where you can download the entire book, freebies as a PDF file. If for whatever reason you want a version that sits on your bookshelf, then there's a link to an Amazon distribution site on the right-hand side. So if you ask, well, what do we mean by big science? I think understandably that's a little bit subfield dependent based on the norms of what people have been doing. But I would say broadly, Modern science involves ambitious projects that are too large and too complicated for any single individual to fully understand and wrap their head around. They require a great deal of investment of time, labor, passion, and funds. That success requires coordination of efforts, coordinating schedules, and optimizing resource allocation. My background is clearly in the construction of large scientific facilities, and so some of what follows is tainted by that perspective. But, think big genetic sequencing facilities, big electron microscope projects, large telescope projects, accelerators, any kind of shared facility, large computing facilities. And that often entails a lot of complicated software. And it's characterized by fiscal complexity, participant scale, and having some kind of management framework. Science isn't unique in this regard. People have undertaken long-term ambitious projects for a long time. Think about pyramids, road networks, building cathedrals took multiple generations, and each of those had their own version of project management. We have successful examples in contemporary science. I think one glowing example is the Human Genome Project, whose goal was to do a full end-to-end sequencing of the genome of an individual person. And that completed ahead of schedule and under budget, in part because the technology was moving so fast, the cost of sequencing came down over the course of that project. Examples of things that are a bit more challenging are NASA's great observatories. The James Webb Telescope, Hubble Space Telescope, Chandra, none of those came in on budget. And the James Webb Space Telescope saw cost growth of about a factor of 10. So 10 times more than people first thought is what it ended up costing. And its launch date slipped by years and years and years. And along the way, it ate the entire science budget at NASA. So the opportunity cost of other things that people couldn't do was really considerable. I think an example of a, recent memory failure was the attempt in this country to build a large particle accelerator that basically collapsed under its own weight after its predicted cost overruns, management concerns, opposition in the scientific community was eventually canceled by Congress, and the leadership in that domain passed to Europe. Certainly for big technical projects, a rigorous approach to project management seems an essential ingredient of success. And the trick there is balancing cost, risk, and performance. One NASA administrator came in saying we were going to do everything faster, better, cheaper. And I think the consensus from that experience was you get to pick two of those, but not all three at the same time. It's often the case that our risk tolerance is lower for big projects. The community wants an assurance of success for a big investment of taxpayer dollars. And at the very outset, picking what are called key performance parameters, which is here are the essential things that we want for this thing to be able to do. And that's a tricky thing because people are going to set key project parameters that they think they can achieve. So they tend to be somewhat conservative because they don't want to fail. But then by the time the project reaches maturity, the project managers are not very incentivized to have the project reach its full scientific potential because they have a clipboard in their hands and they say, well, we achieved the key performance parameters that you guys laid out initially, so therefore we succeeded. So the trick here is finding the sweet spot between scientific aspiration, technical feasibility, and budgetary reality. A lot of scientists hold project management, I would say, in contempt. And broadly, that goes along with negative sentiments towards any kind of management. But my claim would be some kind of management framework is essential as the project scale increases. In my experience, technical project management is really hard and the stakes are high. And if you think about how we go about picking these projects, scientists are notoriously optimistic and tend to underestimate the amount of time and effort it takes to actually get things done. And I think we also tend to underestimate the inefficiencies that go along with these big projects. Every time you turn around, there's another project review. You have to write another report. There's a lot of effort that goes into coordinating meetings. And these big projects are not as efficient as people are accustomed to if they're used to working in small groups. And so I would say scientists fall in two categories: the ones whose estimates you should multiply by pi, and the ones whose estimates you should multiply by pi squared, because I think we're overly optimistic. So if it's all so hard, why would anybody in their right mind actually undertake such a thing? Well, I sort of divide it into two different reasons. One is self-interest, and the other is more altruistic. So from the self-interest standpoint, if you're deeply involved in the implementation of one of these projects, then you're in the most advantageous position to exploit the scientific data that flow from it. Second point, by working on one of these big projects, you gain experience in scientific leadership and working in diverse teams in all sense of the word diverse. Subfield diverse, ethnically, gender diverse. It enhances your skills, and with every single piece of experience, provides a good framework that can be carried forward into other projects. You get experience in navigating human factors and dealing with egos, their priorities, personality quirks. The more people you have, the more quirky people you have. And I think in many fields, career progression is heavily based on demonstration of leadership. And these projects involve an opportunity to exercise leadership at multiple places in the hierarchy. And I think gives people an opportunity to shine and flourish. On the more altruistic side, there's a great piece out of Persian literature where a king is going down a road and comes across a very old man who's planting a tree. And he says, "Hey, old man, why are you planting that tree? Because you're never going to realize the benefits of the fruit that grow on that tree because you're not going to be here to eat it." And the old man says, "You know, my predecessors planted trees from which I benefited, and I'm now planting trees for my successors." And there is an element of paying it forward here and realizing that we all have the benefits of people who sacrificed early on. It gives you an opportunity to make a contribution at a community level rather than just your own individual interests. And it gives you an influence on sort of scientific affairs at a scope and impact level that you're not likely to achieve at the individual level. So in these bits that are coming up here, I would say this project management perspective is a useful perspective to have at all levels of human endeavor that's collaborative. And I would say, you know, things below $500,000, yeah, you can get away without doing this. But as soon as you're in the regime of doing projects with a price tag in the tens of millions of dollars, I think these project management tools are pretty essential. So maybe I'm not going to go through this whole thing, but basically there's this long process of ramping up to do one of these things. This big telescope that we just commissioned has been 25 years in the making, starting with trying to build a groundswell of enthusiasm. In many subfields, there's a decadal prioritization process that actually articulates community priorities that, to my knowledge, started with the astronomy and astrophysics community, but now permeates many fields in the sciences. You need to put together an initial team of people who can come together and try to push this forward. There are some iterations of proposal preparation and going through competitive reviews and down selects, moving on to a conceptual design where the initial cost estimates come from that with an initial work breakdown structure and execution plan, moving forward to a more detailed level of design, moving forward to a final design and construction, moving forward to system integration and commissioning, into some operational phase. And many of these big science facilities kind of never die. They get reinvented, rejuvenated, refunded, and carry on for an extraordinary amount of time, and then eventually get decommissioned. It takes a long time for these things to happen. The big flagship radio astronomy project took 17 years from its initial conception to the first paper. And it's interesting to contrast where we are now with a remarkable technical accomplishment, which was the Apollo program went from concept to people on the moon in 9 years in an era where people predominantly had slide rules, which in retrospect is just extraordinary. So different federal agencies use different vocabulary, and one of the things that we suffered on the project that we did was an inconsistency between the National Science Foundation and the Department of Energy in their sequencing and staging of these different reviews. And if you get going on one of these things, you really have to be prepared for a great deal of time spent preparing for this level of accountability to the funding agencies. And it's their way of getting visibility into the project and tracking progress and assuring that people are attending to commensurate risks. So managing one of these projects really involves three interconnected pieces. One is the list of tasks that you need to do. The second is managing the money with which you're trying to get it done. And the third is the schedule on what time frame things are going to happen. And managing each of those actively is really what this technical project management process is all about. There are some other supporting elements that are important pieces. I'll talk here in a second about what people call a risk registry, which is an attempt to identify and sort of semi-quantify the things that could go wrong, inevitably some kind of safety plan, including cybersecurity. Often there are supporting memoranda of understanding between participating institutions and some kind of decision-making framework that lets you adjust and adapt to things as they move forward. So one of the ways that this task list gets formalized is with this thing called a work breakdown structure, which actually puts together a hierarchical roll-up of all the different bits and pieces that have to happen. So you can imagine data acquisition software, the detection system, the detector system, the project administration parts. People tend to break this into some kind of numerical structure. It goes about 4 or 5 levels deep, and the trick here is to make sure that every single thing that actually needs doing is captured in this work breakdown structure. It has to be understandable. If it's, 48 pages long and nobody can read it, that doesn't help. And then it lets you align the things that are being done with cost accounting, risk management, roles, responsibilities, authority, and accountability. A big part of these projects these days, in fact, sometimes the entire project is software. And one choice that we faced was whether to put all the software under one unifying structure or let the telescope people have their own software and the image reduction people do it in a completely different way. And I think we made the wrong choice. Let me just jump to this one. So here's an example of what's called a Gantt chart that actually lays down on the left-hand column some hierarchical numerical designation of all the different things that have to happen. And then moving to the right is schedule, along with some fraction of completion. And this idea of critical path is that basically at any given time, you can project forward which is the thing that's the bottleneck to progress, right? And identifying those and making sure that those things stay on schedule really lets the entire project stay on schedule. So sort of a word to advice is try to configure yourself so that you aren't working on things that are on the critical path, because that attracts a great deal of management attention. If you're trying to do something that's never been done before, trying to estimate how much it's going to cost is a really tough thing to do. And it's sort of a continuous iterative loop where in the initial stages, there's a cost estimate, but the cost estimate uncertainties are large. And that is in part driven by anticipation of some of those risks actually happening. As the project moves forward, the uncertainty in cost diminishes. But there are lots of incentives in the system for people to underestimate costs. For one thing, if you're putting in a proposal that competes with other people, and if you're the cheapest proposal, you're more likely to be chosen. For another, we all underestimate the difficulty of things. We underestimate the risks. And I think in particular, scientists have a habit to allocate effort to things that are conceptually hard problems and they don't think how much it's going to cost to actually do things by the time the conceptual problem is solved. So there's this sobering record of cost overruns. This JWST Space Telescope is a big success, but it cost 10 times what people thought. The Super Collider got killed, and as the schedule slips to the right, the cost increases because you're paying all these people and you're not getting the work done at the rate that you would have thought. And every single year, most people get a raise. And so there are cost escalation things that add. So how do you do this cost estimation? A couple of different ways. One is to start with this entire work breakdown structure and do a bottom-up cost estimate of guessing how much time each of those things is going to take and do a roll up from the bottom. Another way to do it is to say, well, this kind of looks something like we did before, and we know how much that cost. So let's figure out what the marginal cost is for doing this new thing based on that historical perspective. People also build mathematical models of how much things are going to cost. So for example, in satellite systems, they have basically a spreadsheet, which is how big is your mirror? How much data are you going to move? What's the mass of the satellite? Okay, here's how much it's going to cost you. And there's an example in the book I wrote about doing a parametric analysis of cost of vehicles based on their weight that turns out to be really surprisingly predictive. The different elements in the budget include money for people, money for purchases, supplies, travel, technical services. I think the hardest part of this is budgeting for software. It's really hard to estimate how much software is going to cost, and there are historical examples that are just breathtaking. When Boeing wrote software for the 777, it increased 28 times more than they thought it would. And what often ends up happening is you just hire a certain number of programmers and they do the best they can in the time available, and that's what you got. So my recommendation for software cost estimation is to make a really conservative and pessimistic estimate and then triple it and then add a whole bunch of contingency on top of that. At least in our field, we horrifically underestimate the software aspect. So there is this methodology that people use to track how well you're doing that essentially converts everything into units of dollars. And so the blue line as a function of time here basically shows how much value you've earned in executing tasks. And so this earned value management structure basically says, let's quantify in units of dollars how much it's costing us if we have a schedule slip, which is the vertical difference between the plan and the red line, which is how much you've actually accomplished, tracked in units of dollars. And then the difference between the green line and the red line is how badly you're doing in terms of spending money, because that's how much more money you've spent relative to where you actually ended up. And so it's basically a way to quantify in units of dollars whether something is on track or not on track. And federal agencies pay a lot of attention to this schedule variance and this cost variance. And if it's off track by as much as 5%, they swoop in and start demanding that management take corrective action, because history's kind of taught people that once these things start to go off track, it's really hard to recover and get back again, because that would require that you work at more than the efficiency that you anticipated. So I'm not going to bore you with how these things are calculated, but the bottom line here is it's a way to put progress into units of dollars and track over the course of project execution, whether you're spending money fast enough, whether you're spending it too fast, and whether the accomplishments are tracking as anticipated. The risk to the project can be categorized in two axes. The rows here correspond to the likelihood of something happening, and the columns here, the columns are an indication of what would the consequence be if this thing were to happen. And not surprisingly, the things that are the most worrisome are highly consequential things that are more likely to happen than other things. So things in the top right of this risk management chart get a lot of attention. Things that are in the bottom left get a lot less attention. And people tend to start these projects with a significant amount of contingency money, which is like budget padding beyond what you think it's going to cost to do it. And then that contingency money often gets spent taking action to reduce these risks, to move them from the top right to the bottom left through what's called risk mitigation. And as that moves along, then your exposure to these bad things happening gets whittled away over the course of the project. And a lot of projects maintain this in a pretty formal way, where there's a spreadsheet that keeps track of what are the potential problems. You know, the vendors might not do what we want. Something might break. Some key person might quit. And you keep track. And then this buying down risk is essentially allocating contingency funds to reduce these risks. And at the end of the day, these contingency resources ought to come to zero. NASA has a way of quantifying technology readiness levels about have things been flown in space and shown to work versus someone had some harebrained idea. And from 1 to 9, it spans that range. And the higher the technology readiness level, the less risk there is to cost and schedule. And science people tend to focus on getting the idea and showing that it can work. But history shows that getting things to full maturity, where with high reliability you can fly them in space and make them work, is where a lot of the money goes. So in these big technical projects, there are a variety of ways that the technical facility management is structured. There are highly integrated systems, like the big particle collider in Europe called CERN, where the scientists and the technical facility are fully integrated. There are instances in the second bullet about having federations of existing projects that's sort of like a coordinated activity across different bits and pieces. And at the bottom, our project, I think, is a fairly typical scientific construction project that has a project director, a project manager, a project scientist. And we often try to engineer some kind of creative tension between the science people and the management people so that they argue at the subtask level and try to get to this optimum of performance, cost, and schedule. And paying attention to safety, compliance, and cybersecurity along the way are essential to succeeding. So here's an example of the org chart of the infrastructure at CERN, where you can see it's a big, complicated organization trying to be operated to do science. So shifting from the technical project management aspects to the cat herding aspects of how do you get a whole bunch of random, independent, strongly minded people all moving in the same direction and working collaboratively on a shared goal. There are any number of approaches to this issue about the sociology of how do we self-organize into a large collaboration, going from, on the top bullet, a collaboration, which is a group of people working together towards an objective, to a consortium, which is often a combination of organizations. And the governance structure ranges from old school benevolent scientific dictatorship, where one individual holds all the authority and are individually highly accountable. That's less common. I think in our field, we're moving much more to a sort of shared governance democratic approach with elected boards. And in fact, even the lead spokesperson on the project being elected by the collaboration members. How do you put together the elements of these collaborations? First bullet, membership. So who's in and who's out? And as soon as you draw a boundary of who's in and who's out, you can be sure there are going to be some grinding of teeth of the people who are just on the other side of the boundary of inclusion. And so what are the criteria? How do people get added as members? What do you expect of them in terms of a contribution? It's now common to have a shared code of conduct that people sign on to about explicit expectations for collegial behavior. It's frequently the case that the group includes a specific component who pay attention to attracting and retaining all manner of people in the consortium and making sure that everybody who joins is in a position to thrive. It's a really good idea to have publication policies and authorship policies declared early and have people sign on to a shared expectation of authorship. in my experience, the way we keep score in science is through authorship, and that includes setting out early what is the sequence of authors on a paper. In astronomy, people argue about being first author. In life sciences, people argue about being last author. How are people included? How are they defined? Is it alphabetical? Is it random? That all needs to be sorted out early. In these big projects that rely on some early infrastructure having been built, there's often a recognition that the people who contribute to that pay a significant opportunity cost because they're not off writing science papers in their subfield. And so often they designate what's called a builder status, which is you have the right to add your name to papers that flow from this resource. And what are the criteria for that? But I think we perhaps don't pay enough attention to the allocation of recognition beyond authorship. Who gets to go and give talks at meetings? Who represents the collaboration in outreach efforts? And that's often not as written down and tends to be a little bit more informal. And then lastly, data rights. Who has access to what kind of information when? Are there any proprietary periods? And what's the policy for data release? So how does one, in some, you're a cog in a big wheel, how do you actually effectively contribute to one of these big projects? I would say make sure that the project goals align with your personal and professional ambitions and find the places where that overlap is maximal. Number two, absolutely take early action if you feel interpersonal conflicts are nucleating. I think it's an inevitable feature of these large teams. I think often the biggest challenges we face are human factors and not technical ones. Having a sense of shared purpose and acknowledging the important contributions of others, and stop and check your privilege and make sure that you're contributing constructively, and understanding that people come to these projects with a wide range of backgrounds and expectations. Number three, step forward and help resolve technical disputes as opposed to interpersonal conflicts. Should we use Google or SharePoint, and what kind of detector should we use? And focus on the technical issue, taking into account the cost, schedule, risk, and performance aspects, and frame it as a shared problem to solve and get out of the verbiage of having winners and losers. If you're involved in one of these big facility construction projects, building solid communication pathways with the project managers who are charged with delivering this on time and on budget, understand what their imperatives are, and learn how to speak to them in their own language. These big projects have a heck of a lot of meetings, and I think in many cases the meetings are not run efficiently. So if you come to these meetings, make sure there's an agenda ahead of time, keep the conversations focused, assign action items, and find ways to disseminate information other than in meetings, because that's not an effective use of people's time. And then leave behind a paper trail, because if these projects take a long time, you need to document the decisions that were made, document the code, and make sure that there's a track record of why steps were taken as they were. Specific recommendations for junior scientists, where how do you make a name for yourself when you're part of a big team? First thing I would say is do your homework, read the project documentation, understand what people are trying to do, extend your mentoring network within the project to go in multiple directions and connect with multiple pieces of it. Understand what the internal communication channels are and adapt to them. And if you have ideas in which people can communicate better, go ahead and advocate for them. And then step up. If you find something that needs doing, volunteer for some manageable task to establish your value and to gain experience. Number two, build a reputation for actually doing things. Be one of the people on the project who actually delivers and contributes to it moving forward, and be outward reaching, be communicative, collaborative, and help people align their individual contributions with the project goals. If you can find a place to carve out a leadership niche where you serve as a convener, a coordinator, a collaborator, either formally or informally, to start to build a reputation for being a leader on the project, I think that's helpful. Write a plan for how you're going to be a different person at the end of this endeavor versus who you are right at the moment. What are your long-term goals? What are your short-term goals? How do you want to build your skill set? How do you want to build your leadership portfolio? And then assess your development towards that personal growth plan and seek feedback from people. We don't do a lot of formal performance evaluations in the science community. So I think you really need to be proactive and listen to what people tell you about how to be more effective. A lot of professional progress in science is based on reputation. So do what you can to develop and sustain external visibility, take leadership on publications, be one of the people who goes to meetings and presents intermediate results, and take the lead on coordinating papers that are being authored by the group about how to shepherd a paper through the internal review process, and be one of the people who contributes to individual papers. And then lastly, do what you can to be a mentor to other people. Offer guidance to people who are at the same level in the academic hierarchy as you and below, and strengthen your own mentoring skills, because I think in these team projects, that's another way in which you can both pay it forward and help the project succeed. So let me turn to generative AI, which I think is something that is going to radically change what we're doing in science. And so I saw this paper recently really caught my eye. These people claim to have built a tool which, if you feed it a science paper, will replicate with an agentic AI system the entire data analysis pipeline that was used to generate the tables and the figures in the paper. And that's a remarkable thing. And Nature has actually just recently released an AI boosted assistant to help you write papers, read papers, scan the literature. So I think artificial intelligence is radically changing the way we do stuff. And let me give you a comparison. So in the year 2000, here's what our workflow looked like. We would take images of the sky, we'd run them through some kind of image processing pipeline that would generate a relational database. And that relational database would contain positions, fluxes, time histories of things that were on the sky. And then we do a second stage of analysis that goes to that database and it goes grind, 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 find something of interest. And here's an example of a project that we did, 24 years ago, 25 years ago. And we generated figures and we generated tables and we generated paper narrative as the work product of that whole enterprise. So what aspects of this didn't work? The code generation took the lifetime of a graduate student. There was a lot of duplication of effort. Other projects were writing the same kind of code. We had limited documentation. We had standalone programs that we tied together with shell scripts. And our ability to computational reproduce prior results degraded over a few years because the data and the metadata degrade. We had storage failures, we had data corruption, we had storage medium obsolescence. The data were written on magnetic tape that are just not readable anymore. We had file system failures. The operating system people changed versions of code out from under us. Anybody who knew anything left the project, and we didn't have any standards for data sharing. And the implementation of data mining and astronomy meant the data are mine and I'm not going to give them to anybody. If you compare that to where we, I think, are likely to be in 10 years' time, if you look at the examples that we have, I think we're going to end up with natural language interactions like, I want to make a different version of the plot that has some digital identifier done by my competitor, except I want to change something and do some kind of sensitivity analysis and be sure to do something that I really care about as a natural language prompt to some LLM that will then generate the appropriate reduction pipeline, re-reduce all the data, and give you the answer. So I think this is really going to change the way that we do science and the way that we do collaborative science. So let me just close with this slide and then happily turn to whatever questions people might have. I think we do have this evolving scientific ecosystem. I'm not at all an advocate that the only thing that we do be big projects. I think we need a diversity of scales of endeavor. But there is a trend that I think is inarguable towards larger, fewer teams doing increasingly harder things as being an increasing part of the mix. There's a mixed track record. I think there are examples of these big projects succeeding and not succeeding. I think as scientists, we have a responsibility to step up and engage in the planning, construction, operation, exploitation of these big projects. Navigating the landscape is difficult and personally challenging, but I think being adaptive and attuned and having a good, strong EQ helps one contribute. And I think it's important to keep abreast of developments in generative AI because it's going to change everything we do. And thank you for your patience and death by PowerPoint. Happy to take any questions people might have.
Awesome. Thank you. I have a million, but I will see if I will ask one to get us started, but people please feel free to raise your hand or unmute or just type it in the chat. As the software person in the room, I think you're overly optimistic on GPT's capabilities, but fingers crossed, maybe. But I wanted to know, you made this offhand comment about allowing folks to all have their own software, having one big software bundle, and you said we made the wrong choice, but then didn't say what the choice was. So I was hoping you'd go back to that particular example.
So our project had three big pieces. We had to build a telescope, we had to build an instrument, which was the world's biggest digital camera, and we had to build a data reduction pipeline, right? And the mistake we made was to let the mechanical engineers on the telescope write the telescope control software. We should have let the software professionals write the telescope control software.
So they didn't talk to each other very well, is my guess.
No.
Okay. Okay, that makes sense. Other folks? All right, so Katya in the chat has said, how do political issues affect your work, especially given that CERN is across, country boundaries?
Yeah, so one thing that we didn't talk about that I think is interesting that question prompts is that not only are the projects getting bigger in terms of the number of participating individuals, but also the number of participating institutions and countries. And that adds a really interesting layer of complexity, right? So I'll give you an example. In our project, we had our arms twisted to have international partners contribute to the operating costs of this observatory. One of those international partners was China. When we started, that was a good thing. About 4 years ago, that was a bad thing. And the federal government said, OMG, you can't let the Chinese get all those images of the sky. What if they shoot all our spy satellites out of the sky? We can't let that happen. Therefore, you are hereby instructed to tell the Chinese they can't play anymore, and we, the federal government, will pay the operating costs. So I think it's highly impactful. And I think it's a highly dynamic thing.
Felt. Sending money overseas, especially with the US funder, has been interesting lately, right? Another question from the chat was, how do funders influence? So same idea, but now on the funder side.
Well, at the end of the day, the federal agencies disperse the taxpayer dollars. And so we were fortunate in having proposed a project that aligned with scientific objectives of two federal agencies, right? I would say my own success in writing proposals increased dramatically when I stopped saying, please send me a bunch of money because I want to do this really cool thing. And I started saying, I understand your agency's objectives. Let me tell you how I can help you meet them. And here's how much it's going to cost you, right? Success went up remarkably when I just rephrased things that way. At the end of the day, the golden rule applies. The people who have the gold make the rules.
Fair, fair. Yeah, I resonated with a lot of the comments you had about funders in there. Not the scale, because social science doesn't get funded at $70 million, but definitely a lot of the comments were things that our organizations have dealt with. All right, so how does EDI could be or factored into project member recruitment and selection?
So here's my way of saying this, which I've been saying for many years now, and that is we need to ensure that we attract the best and the brightest to what we do and ensure that when they arrive, they thrive. And I think in the sciences, we've fallen short on both of those counts for a variety of reasons. And I think it is in the long-term interests of excellence and success that we accomplish that goal. Why would we leave aside big components of the population? That's crazy, right? So in that regard, I think we need it certainly in the sciences that I'm the most familiar with, there's a lot of deeply entrenched tribalism and uh, culture of exclusion, right? So trying to do everything within my zone of influence to address that. And I think it's also important to realize that these big projects are training grounds for the next generation. And a sort of implicit goal of these projects is that we build the workforce capability to carry forward whatever the next big thing is. And although that's not often articulated as an explicit deliverable, in fact, it actually is.
Great. All right. So, in your opinion, why do people join in these projects? So, we ask this question a lot in psychology, like why would someone join one of our projects? They tend to be less funded. So, but for your side of the fence, why do people join them? Is it just prestige? Is it the contribution, or does it really matter?
Well, maybe I can't speak for everybody. Let me tell you why I did it, right? It's certainly a lot less confrontational and a lot more satisfying to work in a smaller group of people. And the way I say to my students and postdocs is be very thoughtful about whom you collaborate against, right? And why join this big, huge thing? And the answer is because there was no way to do the science otherwise, right? It just gives you reach into things that are otherwise just not achievable. That's the big overriding reason.
Fair. All right. Let's see if we get maybe one or two more. So, what extent do your collaboration involve researchers from the global south? Or maybe majority world, as folks are starting to call it? And are there governments actually interested in such projects?
Well, there's clearly huge global disparity in the extent to which nations are able and willing to invest in the scientific enterprise, and that's necessarily, in our field, a limitation. Um, we have a lot of engagement from Chile because that's where a lot of current ground-based telescopes are located, and astronomy is actually a priority for them as a nation, sort of a high-tech, tip of the spear technology. Um, the Yeah, so I would say if you want a forthright answer, the sense of obligation in the astrophysics community to address hemispherical disparities is probably not as strong as the desire to address demographic disparities.
Okay, that makes sense. Makes sense. And then I'll ask the last one to wrap us up. If you had to do it again, would you?
Yeah.
I'm not sure I always give that answer, but so
Well, I say that because the thing seems to be working, right? Maybe if it had completely failed, I might give you a different answer.
cool. Oh, so one more came in. Conflicts are evident, right? People, countries, all that kind of stuff. And it's needed to manage at its earliest. So, if and when these conflicts happened, has it ever derailed one of your projects or hugely impacted it? Especially if it's snowballed to like the higher levels.
Yeah, so that's a good question. Let me rephrase, right? Have we ever had interpersonal conflicts actually crash a project, right? Um, Close. But I think often the self-correcting action that happens, I mean, look, I think a lot of these things get going. This is true in non-governmental organizations, in my experience, volunteer organizations, that they get established and get going with some impassioned evangelical proponent, right? Who just drags everybody along with them. And then once it gets up and is starting to become a thing, and it becomes something that you need to operationalize, a lot of the a lot of the personality traits that go along with getting it going are often incompatible with those people being in a leadership role of trying to work with others and making forward progress. And so I think often there's an internal revolution that happens, and those people get promoted into some other job category over on the side, which is actually not operationally influential, right? They get called the chief something or other, right? And kind of get moved over with a little dotted line that comes over and advises people. And they basically get stripped of their authority. And I've seen that happen on scientific projects and in volunteer organizations. So I think the ones that take that internal self-correcting action get past that. It's not quite answering the question, but I think it's adapt or die.
Yes, and I am consistently amazed when I talk to scientists in different areas how much we have similar problems, just with slightly different names and maybe at different scales. But again, I want to say thank you so much for accepting our invitation. It was really fascinating. I put a link to the book from your QR code in the chat if anybody was looking for that. And we appreciate your time.
That's
Thank you.
great. Thanks for the invitation. It was a pleasure.
Thank you.
Take care.
Bye, guys.